Today we'll be reviewing a problem that wasn't on an actual F equals to ma, but rather a concept that has been repeatedly tested on the F equals to ma. The problem goes as follows. Imagine that you have a rod sitting on the face of a plane. The rod has an axis going through its center such that it's pointing towards the viewer, so it's going towards you. Imagine that there's a force being placed on this rod such that it is facing the rod that is hitting a point that is a distance k from the axis. Find the angular acceleration a, alpha, of this rod. Do not use torque equals to moment of inertia times angular acceleration. We can only use the concept F equals to ma. It is also given the length of this rod is L and its mass is m. This is all that's been given. Let's see if we can solve for alpha, even with the small amount of given information. Okay, so let's start from here. Imagine that this rod has been changed by its angle by small angle d theta. That means that this length between its original position of the point on which the force is being hit upon and the final position should be just kd theta, right? Because the arc length is virtually like an arc length, right? And that arc length is so small, it could be just same as the linear length. In this case, then we would say that omega external, well, work external, is equal to F times kd theta. Because kd theta is nothing but the amount of distance traveled, while F is the force applied. But the work is nothing but change in energy. If we differentiate both with respect to time, we get dE over dt equals to Fk times d theta over dt. So let's keep this equation in mind. Meanwhile, what is the energy itself? Looking at this diagram here, we can just express the energy in terms of kinetic energy, which means that if we take every individual particle along this rod, sorry about that, then we end up getting an equation that if a small mass dm is taken on a rod, the energy that small mass takes would be half times dm times omega x squared. Where did I get this omega x squared from? You're probably wondering. Well, if I assume that the angular velocity is equal to omega in this case when it's being turned, then the distance it will be, then its velocity, its linear velocity should be omega x. So therefore its energy will be nothing but the same as the kinetic energy formula. But what is dm? dm is nothing but m over L times dx. M over L gives us the density of the rod, and dx gives us the small length of this piece of rod that we're taking. Which means we can just plug that in here and then solve our integration. We can take out omega squared and m over L outside and half outside, and then therefore giving us the integration negative half to half of x squared dx. Therefore, we end up getting that the final amount of energy is ml squared omega squared over 24. Now let's plug this into our original equation dE over dt equals to Fk times d theta over dt. We end up getting that Fk times d theta over dt equals to ml squared over 24 times 2 omega over alpha. Although I haven't shown that here, I'll still explain how I got that. dE over dt means you're just differentiating E, which we've now found to be ml squared omega squared over 24 with respect to t. ml and 24, these are all constants, but omega itself isn't really a constant, and it's kind of changing with respect to time. It's accelerating. Remember, we're just trying to find angular acceleration. The omega I originally took, it's just happening at a certain point of time. It's not fixed. So what we can do is that we can differentiate omega with respect to time, and that gives us 2 omega times alpha. But remember, d theta over dt is nothing but omega, because d theta over dt just means change of angular distance over time, which is angular velocity, right? So those two cancel out as shown here, therefore giving us that Fk equals to ml squared over 12 times alpha, or that alpha equals to 12 times Fk over ml squared. This is a really important concept, and it's important that you should know how to derive certain things from the basics, which is a good example of what I'm trying to show here today. I hope you enjoyed this video.